sum of 1 over 2 to the I equals 1 to n. Okay, a half plus a quarter plus a 16th, right? That one's definitely a constant, right? If you start at 1, then the sum's 2. If you start at half, it's 1, right? So it's a constant. What about this guy? This is called the harmonic sum. If you don't know it, it's actually ln n, right? Because these are shrinking slower than this, right? Slow enough that it's ln n.
Why is that n before log n? Then before log n?
Well, the intuition is that half of these terms are really the same, right? And so we can talk about the typical one times n over 2, and when the over 2 gets hidden in there. And the typical one is about this size, right? Half of them are about this size, right? Does that make sense?
Yeah.
Well, here, they're really growing fast, right? They're growing so fast that if you take half of them, no, they're really substantially smaller. And it's really the last one that matters at all, right? It's a little bit of integral. In fact, the guy who left us should have stayed for this because, he has to do integral calculus, and this is just basically integrating. Everybody good with that? Any other questions about the test?
I just want to clarify something from this tutorial.
Yeah.
The creation of a cushion without Gaussian elimination. And on the cushion it says you don't need to know how it actually works. But she said on the test she needed to know. So how would you do it without knowing it? Because she's like, well, one of the steps you actually need to know.
Well, one of the steps, it was probably the maintain the loop invariant step. Yeah, so on my answer solution, right, I happen to know Gaussian elimination, and so I forget exactly what I typed in, but I would have typed in more about Gaussian elimination than you really needed to do. And what do I expect to get full marks on that part was really very little. What was, anybody, you remember what the loop invariant was? There was an m, and you were multiplying it by n, and it equaled I, or n prime, right? So without Gaussian, so what you have to do is you have to have a measure of progress, right? And you have to maintain this while maintain this loop invariant while making progress. And I would agree with you. How do you do that without knowing anything about matrices or Gaussian elimination? And really, if you said when I marked that test, if you said, hey, I want to maintain this while making progress, and maybe my progress will be, I don't know, the number of non-zeros, and I don't know, and I would have given you full marks for that. And if you'd said, hey, you do some sort of row operation, then I would have smiled. If I say you don't need to know Gaussian elimination, I mean it. All right? People, and again on that problem, right? Half the class didn't get it, right? I mean, that's just the truth. You had to. I think I gave you the loop invariant, right?
Yeah.
And then you had to think about how to establish it. You had to think about how to get the postcondition from it. You had to remember what the steps were, right? I don't know. Is that hard or is that easy? It's hard for me to think whether even that's hard or easy. Quite frankly, it's. For me, it's so easy that it's hard for me to think about it being hard, but people find it hard. So, I tell you, it is an ongoing challenge for me to write tests which people find easy. So, actually, I'll tell you, I sent Monday's test to Leah, and then this morning I gave it to my girlfriend, and they both said it was too hard. So today I've been kind of giving you a bigger hint and thinking about it more. And
Maybe you should give it to your grade 12 son.
My
If he
grade
can
12
do it,
son.
then we can do it.
Yeah, exactly. Exactly. So yeah, I mean that's the nature of the beast, right? Any other thoughts about it?
When does the section start?
Oh, that's a good question. Good question. Let's talk about that. So on Friday, I think we have pretty good odds that the room is available at 2:30, right? And then it's definitely ours at 3:30, and actually it's definitely ours from 4:30 to 5:30, right? Because they've allowed me to book it for that period, right? I have the room booked every Monday, Wednesday, Friday here. This one, is just the grace of God that we get it. So let's hope that this is available on Monday. And my thinking, unless somebody objects, is in an ideal world you could do this test in a half hour, but we know you're going to want longer than that. So to be fair, I want everybody to have the same length of time. So I'm saying you can use 2 hours. All right, so on the top of my test, I wrote what time did you arrive and what time did you leave and how long was that duration. And I'll try, somewhat try to watch, and if I notice you're cheating, then you'll be in trouble, right? So then you basically have and I don't want people coming and going in the middle, right? Right, for example, if you come in the, because we all get confused, right? So, come at 2:30 and leave at 4:30, or come at 3:30 and leave at 5:30, right? And when you're doing this shuffle in here, be quiet, because people are working. And, if you have to go to the bathroom, don't talk to people who've already left. Pretty obvious things. Everybody good with that? Any other thoughts? You think about that, and I'll try to get this thing going. Come on, hello. No, don't be upset. Oops. Yes, keep thinking of questions. Any other? Everybody kind of good with this recurrence relation? We did this when we left. Everybody okay with this? And this is just the chart of that. All right. Should we go on with recursion? So, sometimes I get as code for a recursive program something that has a loop in it. And, I'm amazed how often, people ask how long did it take to mark. Well, the gestalt, you just kind of look at the gestalt of the page, and often I know whether it's more or less right. For example, if it's a recursive program and it has a loop in it, it's wrong. Right? Let's just be clear about this. It's unless you have, only cases is you need a loop is if you have lots of friends and you need to loop over your friends. Right? Sometimes that happens. But generally, you only have a constant number of friends. And, all right? The other thing that really trick is in iterative programs, you have variables. Variables, what's a variable? It's something that varies, right? In a recursive program, in some ways, there are no variables, right? Nothing varies. You will have things which are called variables, but you give them values, and those values never change, all right? We have things that you declare more than you have, you store things in boxes, but once it's in that box, it never changes, right? So I want the recursive code that I get from you, and pretty well I can't imagine a circumstances will be different than this. I want it to look exactly like this. All right, so let's go over what this means. All right, don't deviate from it, or I could, All right, so the first thing is you personally have been given an instance, right? In this case, you've been given some value of A, B, and C, and you must return some values related to A, B, and C. And for every possible and for every path through here, right, you have to get the right value here. Now, what do we want to document? You focus on your mission. What's your mission? Is I want a very clear statement of what the pre and post condition is. Now, if that statement is exactly what I put in the question, then don't repeat it, because I, as a marker, am lazy and I don't want to read it 60 times. Right? So if it's exactly the same, then you can ignore it. But if you change it in any way, shape, or form, I want to know how you've changed it. All right? So a very clear precondition, postcondition. Right? Then, and these effectively document, what these variables mean and what these variables mean. Right? And how they relate. For example, maybe A is a tuple, B is an integer, C is a binary tree, whatever. Right? Everybody? So, and then you don't have to do things on your own. In general in life, you got to get help from your friends. So, how do you do that? I have my input A, B, C. Somehow I take my input and I do something to cut it, paste it, move it around, and I construct an A, B, and C for my one friend. And I also construct an A, B, C for my other friend, if I have two friends. Right? Maybe I have 3 or 4 friends. Maybe I even need a loop to create lots of friends, right? But not likely. Everybody here? Then, I make sure that these inputs are smaller than my input. These instances are smaller than my instance, right? In some measurable, concrete way. And I make sure that they fit the precondition, right? So this is one way I know that you're messing with me. If you haven't changed the definition of the prefix, and what you write here doesn't meet my prefix, then you're going to lose a lot of marks. Right? Then you take the input that you've constructed, the instances you've constructed your friends, and you give them to your friends recursively, and by magic, your friend gives you an answer. Right? Then you trust him, right? And but you don't expect anything else from him. And then you take his answers and you combine them to get your answer, right? And then you output your answer, right? And if your input is sufficiently small, right, and that's the same definition of small with respect to these guys who are getting smaller, right, then you solve it on your own. Everybody got that? And you can see how each variable is not actually a variable, right? Because it never varies. Right? I mean, you could use the same variable here and here, but why? It'll just mess up, especially since we're not, optimizing code. It'll mess up my reading of it. right? So you rarely have to change the variables beyond their initial setting. It's not an iterative algorithm. Rarely, we don't have any additional local variables, right? Beyond this, you don't have any additional. Sometimes you need extra inputs and outputs. We'll talk about that later. But if you have them, document them. This is a really important one. All right? No global variables. All right? You know nothing about except what comes in through the input. You change nothing except what goes out of the input, right? And sometimes I lie about that. Maybe I'll have a global graph that everybody's looking at, right? Or I'll have a global graph that we're, and I don't, we could put it there and put it here, but it's not really a global variable in that, I don't know, we probably don't change it. It's a global thing that we all look at. All right, everybody go to this? Right, so for example, if a local variable, you have a local variable in and you change it, and you don't pass the new value to your friends don't know it's changed. All right, so, oops, I get trigger happy. So we're going to do sorting, all right? What are the sorting algorithms we're going to do clearly? Merge sort, quick sort, right? So our input is a bunch of numbers. The numbers could be repeated. The output is those same numbers sorted, pre and post condition, right? Right, we're given a list of numbers. Here's a list of numbers. I guess blue in this case means they're not sorted. List of numbers not sorted. And somehow we split them into two sublists, right? We get a friend to sort this one, a friend to sort this. Somehow we take these two and we put it into one list, right? So that's kind of the big picture. There's different ways we could do it. When we split it into two lists, we could split it half-half, or we could split it all n minus 1 and 1, right? That's one sort of, or we could put very little work into splitting. And if we put very little work into splitting, then what you get is actually merge sort. You cut them in half arbitrarily, and then you put a lot of work into merging. If you just split and you sort the first half, and then you insert the last guy in, right? That's insertion sort. The other option is you can put lots of effort into the splitting, right? Quick sort, you partition the guys, and then you put very little effort into putting them back together again, right? That's quick sort. And selection sort, if you put lots of effort into selecting off the maximum, and then sort the rest, then you get selection sort. Everybody kind of got that? We'll look at them again. Here, merge sort. I have this input. I just arbitrarily cut it into half, right? No work. I get a friend to sort the first half, a friend to sort the second half, right? And then I merge the traffic together, right? I take my fingers here. Which are the biggest? This is the biggest. It goes. It goes. It goes. It goes. Right? Everybody can remember merge sort? Oh, that was fast. I think actually it's the same page as this. So in the book, I typed this out 5 billion years ago. It's an example of merge sort. You can trace through it if you really want to. Right? What's the running time? Well, I have two friends. Each is given an input of size n over 2. I personally have to merge. The splitting took no work, right? But I have to do the merging, and that takes work in. Everybody, right? So, everybody know what the running time of this is?
And log in.
It's n log n. So let's think about where that log n is coming from. Look at it, typical level. How much work is done at this level? Well, I have 2 to the I friends, each with input n over 2 to the I. So the amount of work at this level is n. Right? That's true for every level. Another way of looking at it is you take how much work do I have? Well, I have to do work n. Well, I split it. He has to do work n over 2, right? It adds, right? It keeps adds. So every work is effectively work in, and they're log n levels. Right? So that's where we get our n log n. Right? If you remember our chart from before, the input size comes down to n over b to the I, but the number of instances goes up, a to the I, so the work at this level is this. But in this case, 2 to the I times n over 2 to the I just equals n. Right? So they're the same at all levels, and so that's why you get the n log n. And all right, so quick sort. Everybody's, we did in class during our loop invariant thing, we did this method of given a set and a pivot, partition everybody smaller than the pivot and everybody bigger than the pivot. Remember that? And then we get a friend to sort the first half, friend to sort the second half. And now, how do we put the two together? What do we have to do to merge them back together? Nothing. Right? There's a hole there, you put the pivot back. So, there's an example of it, if you want to trace it out. So now we want to choose the pivot element, right? And this is suggesting we just let the pivot element be the first guy in the list. But what's the problem with that? If they're already sorted, then you don't get a good partition. So who do we use for our pivot?
Middle of the...
You could use a middle guy. And the middle guy would probably work pretty well, for a random input. Well, but if somebody wanted to be nasty to you, they could cook up an input for which your algorithm would be bad, right? So what we do is to avoid people giving us bad inputs is we flip a coin to figure out what our pivot will be. Right, so let's think about the running time. The best time is when you always cut things in half. Right? And then you get n log n time as you did before. Right? The worst case is when you only just shave off one guy. Right? So this is a constant, but if you it's going to be work n, then n minus 1, and then n minus 2. You should be able to kind of see that this is n squared work. Right? You're basically doing insertion sort. Right? Or selection sort. So that's n squared work. The expected time, well, you expect it to be kind of here somewhere, right? Or here somewhere. Right? Now, if you were taking this course with Andy, certainly years ago when I first started teaching, he spends a couple lectures working out the expected running time of this thing. And don't want to do that. All right? So, we're going to just wave our hands around. Let's pretend that in the expected case, it was that kind of at the 1/3 mark, right? Because you kind of then we want to see why it's always, if we split it 1/3, 2/3, well, you still have the case that at every level it's order n work, right? Because no matter how you split it, it's going to be order n work at the level. But then how many levels you get? Right, well, this path is going to have more levels than this path, right? But even this path is log n base 3/2, which as far as I'm concerned is order log n. Right? Does that make sense? As long as you do some damage, some sort of constant damage, most of the time, you're going to be done, and there's only going to be log n depth. People kind of follow that? All right, here's a fun algorithm, all right? The input is a set, and it's not sorted, right? And what's the output? And the input also has a number k. And the output can be thought of as this way. Sort the input, and then give me the kth number, right? So it's the k smallest. Right? People understand what the problem is? So if you do it the obvious way, if you sort them, then it takes n log n time. Right? But we want to do it faster. Can you do it in square root of n time? Why not?
You have to go through all the numbers.
You got to look at the numbers, right? You got to look at the numbers, or maybe there was a bunch of zeros in there messing you up. So you can't do it better than n, and we know you can do it in n log n. So just for fun, we want to see if you can do it in linear time. Right? Does it really matter? No, but yeah, you can do it in linear time. All right. So here's the algorithm. The algorithm is ignore the k. We don't care about the k at the moment. Choose a random pivot, right? And partition like we did before, right? And now we partition them, and it turned out that we had 5 elements on the left and the rest were on the right. It just happened that way. And that we were searching for k equals 3, right? Now we want to get a friend to help us, right? And what are you allowed to do with your friend? You can give him any instance that meets the precondition and that's smaller, right? So, what do we ask our friend?
The same thing.
What was that?
The same thing you did to that smaller.
Right. You first think, where is the input? Where's the answer? The answer's got to be over here, right? And if you throw this away, does it change the answer? No. So we just throw this away and give it to our friend. Does that make sense? Everybody kind of good with that? All right, so that was good. You know, we give this to the friend, our friend gives us the right answer, and life is pretty good. All right, so I just changed our, we still have 5 over here, right? But it turns out we're looking for k equals 8 this time. Now what do? What do we give our friend? First off, where's the input? Sometimes it's on this side somewhere, right? So we give our friend this set, and k equals 8? No. What do we give? K do we give?
K minus R.
Exactly. K minus R. K is the third biggest guy over here, right? So we change k to be 3, and we get our answer. Everybody right? So now the joy of this is that we only have one friend, right? And so the work, I drew work in. And, depending on where we cut it, we expect him to do work n over 2, and n over 4, and n over 8, and n over 16. Right? The sum of that adds up to, what's n plus a half n plus a quarter n plus an eighth of an n? N. 2n maybe. Right? It's geometric. All right, so here we have one friend. So, right, it's n plus a half, just as I said, which adds up to order n. What's the worst case running time?
Is this
Oh, this is still doing this, right? If we do, this is a, right? Log a over log b. So we got log 1 divided by log 2. What's log of 1? 0, right? So log of 0, which is we have one base case, right? Which is what we have, one base case, right? So it gets dominated by the top case, and the worst case time though is still n squared. Right? The expected time though is still n. Everybody okay with this?
for the expected time? How did you get 2 over 3n?
Well, it was a big wave in my hand because the true expected time would take a full period. But you can kind of say, well, what's going to happen? You're not going to get it cut in half, and it's not going to be one guy. It's going to be somewhere in here. Where's in here? Let's call it, here I was being a little pessimistic, right? That your friend's this input is of size 2/3, right? I mean, this is being pessimistic. And, right, this is way pessimistic, right? This is, come on, this is going to happen on average, right?
So like, for example, for the exam itself, you're not supposed to...
I'm never going to ask you anything this hard.
Oh, okay.
No. All right. Yeah, if you can't get it from the chart, in terms of this, every recurrence relation I ever ask you, you can get it from the chart. All right, so here is another problem. I'm given a value b and a value n, and I want to compute b to the n. Oh, and this n here, I don't know why this n's different than that n. Ignore it. I'm sure it's supposed to be the same n. All right. So what's the obvious algorithm, right? If n is 0, I will put 1, and otherwise I cut my number in half, my n in half. I get my friend to compute b to the n over 2. Another friend to compute b to the n over 2. This one rounded down and this one rounded up in case it's not even, right? And then I multiply their answers together. Right? Everybody kind of good with this algorithm? Right? What's the running time in this algorithm going to be? What's the running time if I simply multiply, how many multiplications? If I just do b times b times b times b times b, I'm going to have to do n multiplications, right? N minus 1 multiplications, right? How many, do we have any savings here? Did any multiplication go away? Or did I just pass them on to my friends? Right? I had these n minus 1 multiplications to do. I kind of gave half of them to this friend and half of them to this friend, and I took one of them for myself. Right? So it's not like any of them really went away. So we're going to see that actually the time isn't so good. So here I have n. I asked my one friend to compute b to the 3 and b to the 4. Right? This guy somehow computes b to the 3 and this guy computes b to the 4. I multiply them together and get b to the 7. Right? That's the algorithm. And if you put the whole tree, it's like this. What's the running time? Well, I have two friends, each given an input of half the size, right? I do a constant amount of work. So, so the number of base cases is n to the log a over log b. Well, a and b are the same, so it gets you into the 1, right? We have n base cases. So it's going to get dominated by the base cases, and the running time is n. We didn't really save anything in the number of multiplications. And then if we go back to what we were doing on the board over here, right? The input size is log AB plus log n, right? So the running time is exponential in the number of bits. Yeah? People kind of follow this? I mean, these are two different issues, right? What were the issues here that we're learning in this example? One, if I have a certain amount of work, and all I do is I cut the work in half and give half of it to one friend and half of the work to the other friend, work didn't go away, right? There's going to be no savings in time, and there's no real advantage not to just simply do it yourself, right? That was the one lesson. And the other lesson is we verified that using recurrence relations. And then, just for good luck, we put it in terms of bits again and reviewed that little thing. Everybody kind of got all these the lessons here? As a general rule, I want you guys to ask more questions. Because I'm going to talk fast, and you guys have to ask more questions. Right, so one thing you absolutely have to make sure before I change the slide is you have to think, what is the point of this slide? And do I get it? Right, do I get the point of the slide? And if you're missing some of the details, right, maybe that doesn't matter as much, so you can ask about them if and I'll either say, yeah, whatever, that doesn't really matter that much, it's not the point. Alright, so everybody kind of get the point of this slide?
So, say you have get the running time from the recursion relation, you would have to actually use
The chart.
yeah.
Yeah. What you would do is you would say the number of base cases is into the log A over log B, right? Which is into the 1, which is in. The number of work I do is 1, which is into the 0. This is clearly dominated by the number of base cases, so it's clearly in. And then you would think, what's the size of the input, right? And you would relate the running time to the size of the input. And that's what I would want you to do on an exam. Does that make sense? All right, so maybe I should. Come on.
I hate you. I do. I hate you.
All right. I don't know if you saw that last slide or not. You had a bit of time. Anybody think of how are we going to make this faster?
Instead of dividing by 2 and calling 2 friends, divide by 2 and call 1 friend and multiply that by itself. And if it's an odd number, do it times itself.
Right, exactly. You know, it's the same trick we did before. We either want to make the input smaller than we did, right? We either change this, which we don't know how to do here, or we change this, right? We need fewer friends. How can we have fewer friends? Well, they're really doing the same work. You know, except for this round down, round up stuff, they're doing the same work. So what we do is we round down and we ask our friend once, right? Here we have 1 friend. And then you square it. You take his answer and you pretend you got it twice. And you square it, and if it's odd, you have to bring in an extra beat. Right? So here, if I'm doing 7, then I ask my friend about 3. He gives me b to the 3. I go b to the 3 squared is b to the 6. Right? Times b is b to the 7. Right? And now the running times, you know, we only have 1 friend. So how many, if we do the you know, log A into the log A over log B, how many base cases do we have? We have 1 base case. Log A is now 0. Right? We have 1 base case, and I do work 1. So what's the running time? What happens if all of the work at every level is now 1? Right? So if the work at every level is 1, then the running time is, right? It goes down. The N, capital N, goes down by a factor of 2 each time. Right? So you get log N. If you look at the chart. I don't know if I bring the chart up here. I should bring the chart in here. It says you look at into the log A, look at log A over log B, and you compare it to C, right? And if this one's bigger, the answer is this, the number of base cases, right? And if this one's bigger, the answer is the f of n, which is into the C. Right? And if they're equal, then the answer, well, these are equal, so this times log n is the answer. Right? So it's, in this case, it's 1 times log n is the answer. Did I completely lose everybody on that?
Yeah. You lost me at the, if they're equal, why do you multiply it by log of n?
Well, if this one's bigger, right, we have all these levels, right? And if this one's bigger, then the levels are changing exponentially, so it's dominated by the bigger one, and this is the bigger one, right?
Yep.
And if this one's bigger, then they're shrinking exponentially, and so it's dominated by the work at the top level.
Okay.
And if they're equal, then all levels are more or less the same. Right? It's kind of like why does merge sort in log n? Right? Because it's in work at every level. The top level, I do in work. Right? At the bottom level, I have in, they're in base cases, each do work 1. Right? So either way, it's at every level, it's work in. Right? At the ith level, they're 2 to the I guys who do work. Right? There's this many input, many stack frames at the ith level. Each one is given an input of size this. Right? So you multiply these, and you get in work at every level. But then how many levels are there? Right? They're log n levels. Right?
But every time times log n, not the log n.
Over here.
Yeah.
Yeah, over here, there's work in at every level. Right? Well, here, I don't know, the work is you're dividing by 2. Maybe you should be charging more for that, but I was just charging 1 for saying 1, what work do I do? You know, I was just charging for multiplication, I was just charging 1. 5 minutes already? Holy cow. All right. 6. Watch yourself. All right. So now, since the running time is log capital N, but the size of the input is log n, you know, it's linear. Right? And to be fair, this algorithm is kind of silly because as you keep multiplying, exponentiating, the numbers you're multiplying get bigger and bigger, and so you should be charging more and more for multiplying. But this is exactly what happens in some cryptography things, where we're not multiplying real numbers, we're multiplying over some finite field, and it's really easy to do exponentiation, but it's really hard to do reverse, you know, to do discrete log. And so this comes out. Everybody kind of follow this example? All right, 6 minutes. All right, it's 5 minutes.
Since a lot of problems can be solved, or a lot of recursion problems can be solved with iteration, and vice versa, if you don't know the solution, is there a good way to know which one you should try first? Because sometimes doing the iterative version is actually a lot faster and saves a lot more space than a recursive variant. Or do you just flip a coin, pick one, and go?
Well, you're right that anything you do recursively, what is recursion but a stack? If you bring in a stack, you can do it all iteratively. And in fact, my understanding of compilers is that a good compiler, if you write a program that's recursive, it turns it into an iterative program, right? Because it doesn't have to keep track of these stacks. It keeps track of what this, and so I would say that you write a recursive program if you think it'll be easier for you to do it, right? I mean, it's often easier to write a recursive program when there's sort of this recursive structure to what you're doing, and it's really natural to write a recursive algorithm, and it's clearly easier. And if it doesn't seem like it's clearly easier, then don't do it. Often it's easier, right? I mean, sometimes it's easier. But actually, to tell you the truth, I've also heard people who say, okay, you know, in computer science universities, we do these Ivy Tower things, and we do things like recursion, and we do things like dynamic programming, and you know, 90% of the people who graduate in computer science go work for the bank. And they translate this data into this data, and never in that translation do you use recursion or dynamic programming, right? So it could well be that if you work at a bank, nothing you do in this course will be useful. But if you work for a bank, you know it'd be boring. All right, so this is kind of a good intro to this topic, which we now have 3 minutes to talk about, which is you want to write recursive programs. when your data structure is recursive, so that it really lends to recursive programs, right? And what's a good recursive data structure is a tree. All right, so I asked one term, give me the definition of a tree, and nobody in the class gave me an answer that I thought was a good answer. All right, so here's my definition of a tree. We got a binary tree if it's either the empty tree, right, because the empty tree is a tree, or it's a node that has a left subtree and a right subtree. Right, so that's a recursive definition of a binary tree. Right, why is this a tree? It's a tree. This is a tree because it's a node with the left and right subtree. Right? Why is this a tree? Because it's a node with the left and right subtree. Why is this a tree? Because it's a node with the left and right subtree. Why is this a tree? Because it's the empty tree. Everybody kind of got that? So, in the remaining 1 minute, we can count the number of nodes in this tree. All right? And let me tell you something right up front, which I didn't really think about telling people until I was marking last term. So maybe this is the first time I did it. When you think about doing recursion on a tree, think about it as you personally know the root. You're going to think about the root. You're going to give your left subtree to your left friend, and your right subtree to your right friend, right? And now assume that your right friend doesn't know the root and doesn't know the left subtree, right? The only communication that goes on is through you, right? You have to give whatever your left friend needs to know, and then your left friend gives you whatever you need to know. And then your right friend, you have one conversation with your right friend, and then you have to put the pieces together. All right? So in this case, what's your left friend? If you want to know the number of nodes in the tree, what does your left friend tell you? Number of nodes. And what does the right friend tell you, the number of nodes? And what is your answer?
Plus 1.
Left plus right plus 1. Right? Everybody kind of got that? We out of time, probably.
Yep.
Everybody good? All right, so I'm going to see a certain number of you at 2:30 on Monday, and the rest of you at 3:30 on Monday. And if you really panic over the weekend, you can send me an email or even give me a call. I'm at home. Actually, I might go out on Sunday, so you're better off tomorrow.